of values, an ordered set of values. That is, we know what number is ascribed to be x1, what number is ascribed to be x2, and so on and so on. So an ordered set of values, which, of course, if we put in these equations are satisfied or become true identities. So a solution is evidently an ordered set of values, ordered set. The order matters. So how to solve these systems? There are many different methods. We will only consider three main methods. Out of these three main methods, only one is universal. Only one method works well all the time. We can get a decent answer for any system of equations. Today we will consider those, let's say, not so universal ones, not so universal equations, and see a couple of methods that are good methods for solving systems of equations, just not exactly all systems. So, for example, if I have this system, we see you have two equations and three unknowns, three variables. So this system actually has solutions like 1 to 10. If we put x is 1, y is 2, z is 10, you get both equalities correct. Or maybe 0, 1.75, 8.22. Again, if you put these values into the system for x, y, z, you get true identities, correct identities. This means that these both ordered sets are solutions of this system. It doesn't mean that it doesn't have any other solutions. It does. It has as many as we like, infinitely many solutions, in fact. But, well, this might be an example. So I don't say 2, 1, 10 or 10, 1, 2 because the order matters, as we saw, ordered set of values. It is important which is x, which is y, which is z. Okay, that's the general stuff about systems of equations. So the not so general stuff, still some more general stuff, right? Matrix form. We could think that these coefficients, a11, a12, are the coefficients, these would be the coefficients of the first equation, these would be the coefficients of the second equation, and so on. So m rows for m equations, and in each row we put all the correct coefficients in the correct order, and then we think that we have the unknown column matrix. A single column consisting of all n unknown numbers, which have to be found, the variables, and the right hand constant column consisting of m constants. So what we actually have, an interesting thing, if we multiply matrix A by matrix X. Remember how we multiplied matrices? We said we took first row and multiplied those elements one by one through the first, or in this case, the only column. Remember that this first matrix is n by n size. The matrix X is n by 1. So these numbers are indeed equal. And the resulting matrix is size m times 1. In other words, if I multiply these elements, the first row of A and the one and only column of X, if I multiply those, then in principle I get the left-hand side of my equation. If I go back, I get the left-hand side of the first equation. See, the elements of the first row of the matrix A are multiplied by the complete column of the matrix X. And similarly with the rest, the nth row gets every row gets multiplied by the one and only column. So we get the left-hand sides, and then the right-hand side numbers are given. So in principle, that system that we saw in the previous slide can be indeed written as matrix A times X equals matrix B. Here, again, X and B are column matrices, although different sizes. But we can write a whole system of equations in matrix form as a single matrix equation. But of course we must know what the matrix A is, what the matrix X is, and what the matrix B is. However, this matrix form is often used to describe a linear system of equations. Now we have several names. I will erase evidently what I have, erase all ink. So consistent system. A system is called or said to be consistent if solutions exist. If there are solutions, maybe one, maybe more than one, but it's consistent. That is, there's no contradiction in the system. Solutions exist. There are some sets of numbers, x1, x2, and so on, until xn, that can be put into this system, and the correct equality for each equation is obtained. One, maybe more. Consistent simply means yes, something exists, some solutions exist. How many? Doesn't say. And we say inconsistent if it has no solutions. That is, if there's no such set of numbers, x1, x2, and so on, that we could put in all equations simultaneously and get true equalities all at the same time. And now today we have a couple of methods that work, but they work in, let's say, specific situations. They don't work just at any moment. So Cramer's method, let's consider first of all the simplest system. Let's suppose the simplest system, a 2 by 2. I actually named them x1, x2. I could name the variables x and y. Of course, yeah, that's not a very big problem. So the system matrix is A. In this case, the system matrix would be matrix, so I'm using the round parentheses, A11, A12. The system matrix is the matrix of the coefficients in the correct order. And the system determinant would be the determinant of the system matrix. Simply the determinant of the system matrix. We oftentimes denote determinants by the Greek letter delta. Now we do an interesting thing. We find another determinant that looks like this. What happens here? In the first column, instead of the coefficients at x1, we have put the matrix B elements. We simply put these elements inside the original system matrix. We simply replace. The first column is being replaced by the column of the free elements. And similarly, we make another determinant. So now we have two determinants, three determinants actually. We make a third determinant where we substitute the same B column, but we substitute it this time for the second coefficients, for the second column of coefficients. So for A12, A22. In the main determinant. So now we have three different determinants, and interestingly enough, it turns out that the values x1 and x2 can be found by dividing the values of these determinants, these special determinants, delta 1 and delta 2, divided by the system determinant. Remember that a determinant is finally, in the end, it's a number. So x1 and x2 can be actually found by dividing these determinants. This method actually is the thing which in fact gives us reason to define determinants as we do them. So first of all, I will give you an example, and then I will try to explain how we come to this result, how we arrive at this result. So first of all, an example, this one. So the system matrix would be 3, 1, 1, minus 2. The system determinant, 3, 1, 1, minus 2, is minus 6, minus 1, that's minus 7. Now the determinant for x, I'll write delta x. Determinant for x, I will not write 1 and 2 because I have names for those variables, not numbers. So I replace the first column, that is the column of coefficients at x, by the free column, by numbers 1 and 5. So I have 1, 5 instead of x coefficients. And for y, I still have 1 minus 2. At this moment, there are oftentimes mistakes. If you see a variable without a coefficient, if you see a variable without a coefficient, please remember that this means that its coefficient is 1. And you have to put 1 in the matrix, like here and like here. So that's of course essential. We don't write x, we don't write y ever, but what we do is we use these 1 minus 1. And sometimes when an element is missing, a variable is missing, we actually put sometimes a 0. We will have those examples today. And now we have minus 2 minus 5 is also minus 7. And then the third determinant for y, we take the first column from the original matrix as it is, but now we substitute the second column coefficients by numbers from the right-hand side, 1, 5. And we have 15 minus 1, that's 14. And so we see that x has to be delta, determinant for x divided by delta is minus 7 divided by minus 7, it's 1. And y is evidently the determinant for y, the last determinant we found, divided by the system determinant, and that's 14 divided by minus 7, that's minus 2. So the solution, the answer, would be 1 minus 2. X is always first and y is always the second. Yes, of course, you can tell me that we can solve the system using school methods, whatever we did at school, it is possible, and I would say, yes, I agree, but sometimes, so imagine that you just have the coefficients, not 3, 1, 1 minus 2, but something worse, like 47, 34, 18, 39. If you have numbers that are not nice, then solving the system by the school method will simply be very clumsy and uncomfortable. We do exactly the same thing when we find the determinants. We do exactly the same thing. Now I will try to explain how exactly we come to these solutions. So where these determinants actually come from. Is everything? And actually I don't want this as well. Okay, I don't want this, but I want the original system. So suppose we want to eliminate x2. Let's suppose I want to eliminate these terms. What we do normally with school mathematics, remember what we did. So, okay, I will. All right, let's have the system. What we did was, for instance, we multiplied the first equation by 2, looks like, and so we had 6x plus 2y equals 2, and then when we add this first equation and the second equation, now we have 7x, y's disappear, minus 2y plus 2y, they disappear. But this is what we actually did, more or less, to exclude, for example, to exclude y from the whole system. We actually only needed to find appropriate factors for these equations, and then we could add them up and exclude, get rid of one of those elements, one of those unknowns, one of those variables. And so I once again, I have to go back and erase my scribblings. So let's suppose I want to get rid of x squared. So I would multiply the first equation by A22 and the second equation by minus A12. I choose minus because I want the products to have opposite signs, these products. Now the first equation becomes A11, A22, x1 plus A12 times A22 equal times x2. Okay, I'll let, okay. It's always the problem of notation. I want to do things in the simpler way, and sometimes something simply gets lost. So this is x2, and on the right hand side I have b1 times a22. Now to get the second equation multiplied by a12, I have a1 minus a12 times a21 times x1, and here I have minus a12 a22 x2 equals minus b2 a12. And so what we have when we add these equations, so it's still the same system. You know that we can multiply an equation by whatever number if it's not zero. Now we can add up these two equations, and when we add these, we see how these two elements, these two products, will actually cancel out. And so I have x1 multiplied by, if we add these, I have a11, a22 minus a12, a21 equals, and on the right hand side I will have b1, a22 minus, sorry, this was b2, minus b2, a12. Now just think about what we have here. So x1 would be b1 a22 minus b2 a12 divided by a11 a22 minus a12 a21. But if you just look at the bottom part, you have a11 a12 a22 sorry, this is a21 a22. See what we have there. We have exactly the system determinant. So you see, these determinants don't come from nowhere. They come from the method of normal solving these equations normally. If I had numbers, of course, instead of those a coefficients, it would be very easy to see. But if we do it like this, a little bit theoretically, if we consider the general form, you see that what you generally do at school when you solve a system like this, like, okay, 3x plus 5y equals 1, 2x plus 7y equals, I don't know, minus 3. This is what you do. To eliminate y, you would multiply the first equation by 7 and the second equation probably by minus 5 to get negative, the opposite. So 35y and minus 35y, when you add, they disappear. Interestingly, you would actually discover that the system determinant is 21 minus 10, that's what is this, 11? And it also shows up when you multiply these numbers. And now here we see what's different between the top and the bottom part. What's the difference between the top part and the bottom part? We see that in the top part, instead of A11, we have B1. And here, instead of A21, we have B2. So instead of A21, we have B2, and instead of A11, we have B1. Exactly what I have in my general method. And so, which side looks nicer? I would say definitely the side with the determinants. And therefore, it's a very good idea not to do this every single time with numbers specifically, but just look at the determinants. Don't mess with the system on the whole, but just look at those determinants. So with x2, if I want to eliminate x1, then I would multiply both equations, one with a22 and with a12. Sorry, no, with a21 and a11. And again, in a similar way, we would discover that in the quotient denominator, in the divisor, we get the system determinant, actually this expression, and in the top part, we would get this second additional determinant. So this might be, let's say, at least a partial answer to the question that came up last week, I think. Why do we find the determinants this way? That's why. Because the determinants originally come from system solutions. If we solve the system, then we can actually show that, okay, let's write it like this, and let's call this expression determinant. Let's call it determinant. And that's it. But we start in mathematics nowadays, of course, we start from the other end. We say, okay, let's call this construction, this construct a determinant, and let it be found this way. Let it be found by this method. However, the method and the idea at all comes from solving linear systems. Now, a big question is, so what if the system is bigger? What do we do if the system is, for example, a 3 by 3 system? So what we do, we still have a system determinant. The system determinant consists of all the coefficients in the system, in the left-hand side of system. Then, of course, what we do next is find those additional determinants, and we do it like this. So I specifically now color the right-hand side column red, because for finding the first unknown, we replace the first column, the elements of the coefficients of that element, say of x1. All coefficients of x1 are in the determinant. They are replaced by this red column from the right-hand side. In the determinant for the second element, for the second unknown, for x2, we replace only the elements of that column by the red column, by the three elements. And to find the third unknown, we again take the system determinant, but this time we replace the coefficients of the third element by the free column, the right column. See, we put back the white numbers are what we leave in place. So the second and the third column stay as they are in the system determinant. We only change the first one. In the next, now the first and the third stay the same. We only change the second one. And in the third one, the first and second columns stay the same, and we only change the third one. And how do we find the unknowns, the variables? Well, like this. Exactly like this. Again, it can be demonstrated that the same idea works out. The demonstration would be rather complicated and much more difficult than for the system of two equations with two unknowns, but in principle it would be possible, and it is possible, to show that, again, this division of determinants works. So it's always the corresponding determinant where the column of the coefficients of the relevant variable is replaced by the B column, always that, and that determinant is divided by the regular normal system determinant. We can see, of course, that this doesn't work always. We can see that evidently it only works if the determinant, the system determinant, is not equal to 0. And this method also only works if we have an n by n square matrix. That is, if we have n equations and we have n variables. If the number of variables and equations is the same, and if the system determinant is not equal to 0. If the system determinant is equal to 0, we have to do something else. This method will not give you solutions. So the system determinant, if it's not 0, then we can find the solutions by Cramer's method. Cramer's method, or actually these are the Cramer's formulas. The method is method as it is, and the formulas are specifically these special determinants and the quotients of these special determinants. Let's try it. Let's try it. So the system matrix, we see that the system matrix is 2 minus 2, and the third coefficient is 1. Next, 3, 1, minus 2, and then 1, 3, minus 4. That's the system matrix. Now we can write down all the determinants. Oh, I can also write that, of course, the unknown matrix is x, y, z. I can write it down. So I don't have numbers for the elements. I have names, x, y, z. And of course, the right-hand side column is 7, 3, 5. So these are the elements. If I want to write the system as ax equals b, then these are the a and x and b as they are. Now let's write the system.
Ma'am?
Yes.
Ma'am, I think it's b equal in b. I think it's minus 5, ma'am.
Yes, it is minus 5. Yes, right. Thank you. It's minus 5. All right. So I would still have. When replacing, I would still probably by habit I would look at the system. I don't particularly write this. I'm writing it now simply to draw an example, to show you an example. What is A? What is X? What is B? Now, how do we use this? So the system determinant would be 2 minus 2, 1, 3, 1 minus 2, and 1, 3 minus 4. So let's suppose, let's be, is it lazy? I don't know. Let's use this diagonal method, that is, the situation where we actually copy the first column, 2, 3, 1, and the second column, minus 2, 1, 3, and we draw those diagonal lines. Okay, back. Draw these diagonal lines so that we can find the product. So let's see, green. Okay, this will be positive product, this will be positive product, and this will be positive product. Be very careful when you draw the lines. Don't be sloppy, don't be careless. Take care which actual factors you are multiplying, through which point you go. So 2, 1 minus 4, the product is minus 8. Minus 2, 1, the product is plus 4. And 1, 3, 3, the product is plus 9. Now we go back and we have a look at this opposite subtracted product. So we will subtract 1, 1, 1. That's 1. 3 times minus 2 times 2 is minus 12. And minus 4 times 3 times minus 2, 8 times 3 is plus 24. And we can find the determinant. So you see, it's a lot to do with finding determinants. You have to practice finding determinants, and this means that the question in the unit test next week, if you see Cramer's method, then you know that first of all, I am checking how you find the determinants. I want to see how well you can find determinants, and then the rest. So we see 13 minus 8. 13 minus 8 is 5. And here we have 12 plus 1 is 13, so minus 13. This determinant looks like minus 8. I hope it's correct. Because if a determinant is not exactly correct, then we might have sometimes a problem. So determinant for x, we replace the first column by 7, 3, minus 5 by the big column, and the rest remains minus 2, 1, 3, 1, minus 2, minus 4. Now we can use another method, whatever method we like for finding this determinant. For example, I could make 1 in the top left corner. That would be row 1, remember, minus 2, row 2. That's like playing around a little bit. How to make 1 here? I want 1 because I want to eliminate those other numbers. So row 1 minus 2 times row 2. Yes. 7 minus 6 is 1. Minus 2 is minus 4. And 1 plus 4 is 5. And then we have 3, 1 minus 2 as it was, and minus 5, 3 minus 4 as it was. Now we can make zeros below 1, or we can make zeros in the first row. It doesn't matter for the determinant. For finding the determinant, it doesn't matter which way we go. But, okay, let's go this way. So let's say column 2 will be column 2 plus 4 column 1, and that makes 1, 3 minus 5 unchanged. But column 2 now becomes multiply by 4, add there, it's 0. Multiply by 4, 12, plus 1 is 13. Multiply by 4 is minus 20, plus 3 is minus 17. And similarly, column 3 could be, let's say, subtract 5, column 1. We need to subtract 5 from 5 in order to make a 0 there. So first column will be multiplied by minus 5 and added to the third column. 1 times minus 5 is minus 5 plus 5 is 0. 3 times minus 5 minus 15. Go on to the right, we have minus 17. Minus 5 times minus 5 is 25. Added to minus 4 is 22. And so in this case, it looks like we have expanding through the first row, we have 1 times 13 minus 17 minus 17, 22. These look like all full numbers. So 13 times 22, 26 and 260, that would be 286 minus, and this minus 17 squared is 289, so this is minus 3. So there might be some problems with the first one, possibly. So these are not the nicest numbers, so I'm not exactly sure where I made a mistake. I suspect that there is some arithmetical error, but for now we can accept it as it is. So we would also be able to find the second and the third determinant. I am not, at the moment, I am not doing that on the board. I'm just going to write down those determinants. So in the y determinant, 2, 3, 1, now the second column is replaced by 7, 3, minus 5, and the third one is again the old one, 1, minus 2, minus 4. And for the z determinant, so again, as soon as we find this, we will be able to move on. And finally, the z determinant, something wrong with my tablet, it's acting up a little bit. The first column is as it is in the main determinant. The second column, minus 1, 1, 3, is the same, minus 2, 1, 3, is the same as it was in the main determinant. The third column is now replaced by 7, 3, minus 5. So it's again some number that can be computed. And as a result, the x value would be minus 3 divided by this system determinant. At this moment, it looks like it's minus 8. I'm not going to recalculate. I might be mistaken. Y would be, again, the y determinant divided by the system determinant in my version it's at the moment minus 8, again we would be able to find the value. And for z, we would take the z determinant and again divide by the system determinant, which looks like minus 8. I'm not exactly sure if it's correct. Minus 8 plus 4 plus 9. 13 minus 8 is 5, that's right. And then 12 and 1, 13. Minus 13 minus 8. So possibly I made a mistake somewhere, maybe with those columns, because normally we deal more with row operations rather than column operations. It is possible that I have made a copying mistake somewhere. So that's not the point at this moment. So arithmetical mistakes happen. This is why, unlike elementary mathematics, in main mathematics you may use calculators. In main mathematics you may use calculators, so that should not be a big problem. 21 instead of 22. You think this one. Let's check. When we take okay, we had this multiplied by minus 5 is 25, added, yes, that's 21. You are correct, that's good. So 21 times 13 is 13 less than this, so that would be 7, 3, okay, 2, 7, 3, and then it's minus 16. And then, of course, it's perfectly beautiful. Minus 16 divided by minus 8 is actually 2. That looks more likely. And similarly, we find the other two determinants by whatever methods we like, by whatever methods you prefer. We could, for example, in this x determinant also, we could take this and add down to make zeros below that 1. Not to make 1 in the top left corner, but use 1 that we already have. Because our only goal at this moment is to find the determinant. And similarly, I can use 1 to make zeros below it and to find the next determinant, so to find the y determinant. Or you could take 1 from z determinant and add it up. It doesn't matter. Remember that the determinant can be expanded through whichever row, whichever column you like. The trick is that if you have Cramer's method for a 3 by 3 system, you have to find 4 determinants. For 2 by 2 system, remember, you have to find 3 determinants. If we have a system of 4 equations and 4 variables, a 4 by 4 system, then you need to find 4 big determinants. 4 determinants that are 4 times 4, 4 by 4, large ones. So what that would be, of course, harder. The bigger the determinant, the harder it is to find it. But the rule, the method is exactly like this. Now, to recap, only for square matrices, so only if the number of equations and number of the variables is exactly the same, the determinant cannot be equal to 0. If it is, then this method doesn't work at all, again. And basically that's it. Okay, now the next one, inverse matrix method, or sometimes simply called the matrix method, but I do like inverse matrix method. So we still think in terms of matrix product. Okay. And to use matrix method, we think about matrix operations again. So we would say that we start with a system, thinking of system as,
Excuse me, ma'am.
yes,
For the last one, when the first determinant is equal to 0,
then
uh,
it doesn't, then at this moment, this method does not give us any answer because you cannot divide by 0.
does that mean that equation doesn't have a common solution?
Um,
Or or we need to find it
necessarily.
by other
So
methods?
we can do other things. Basically, if this determinant equals zero, then it's one of two possibilities. Either the system has no solution, it's sometimes possible, or another possibility, it has infinitely many solutions. You cannot get one specific solution. So determinant equals
Okay.
zero in principle means that the system might have no solutions or might have infinitely many solutions. It simply means it doesn't have one unique solution, but what other options there are, which other option is true, this method doesn't tell us. But the thing
Okay.
is that,
So when
yes,
determinant is not equal to zero, we have a specific solution.
yes,
Otherwise, it
yes,
can be a parallel line
yeah.
or lines in different planes.
Yes, because these are equations of planes. For example, right, one solution means that we have three planes that intersect at one point, like the corner of a room, where the two
Okay.
walls and the floor come together. One point of intersection of three planes. But if we have no solutions, it could be either three parallel planes or two parallel and the third plane intersects them, but there's no point belonging to all of them. That's what
Okay, fine.
it means.
So can we have any ideas about Kramer's method giving such an idea about they are in different planes or in they are parallel?
We will see there's another method. By other methods, we will be able to see that this zero determinant, in principle, only means the main thing that it means if the determinant is zero, there's no one certain unique solution. Which case it
Okay.
is, no solutions or infinitely many solutions. Kramer's method simply doesn't give us the answer. There's another method that will give us the answer.
Okay, fine. Thanks.
Okay, now we go on to the matrix method. So the matrix form, we always think of this equation in the matrix form, AX equals B, but because we will need to find the inverse matrix, again, this will also work only for square matrices. Only for square matrices, that is, n equations and n unknowns. And again, you know that the inverse only exists if the determinant is not equal to zero. So these two methods actually tell us the same thing. If the determinant is zero, then we cannot find a single solution. It's either we cannot find a solution at all, or we can find maybe infinitely many. And so if we have written the system in the form AX equals B, then we think if we know, at the moment this is simply the theoretical part, we will not in fact follow through all steps, we will just get to the point, finding the inverse matrix. We can multiply both sides by A inverse, but from the left. And then we get,
Well, I have a question.
yes,
Um, if we get a zero determinant, right, in the exam, what will we say? We will say the soli-
this,
the
this,
mat
this
the
has several possibilities. So one possibility is that I have deliberately set this up so that you see, okay, zero determinant, this method will not work, but I know which method will work, and you will know which method must work.
Oh, okay,
Another
okay. So
possibility,
if it didn't work, we use another method, right?
you could have anything in the examination, but you have to understand if the zero determinant, if you have a zero determinant, and if it's correctly found, and it is indeed zero, it means that these methods will not work, but there is another method that you have to use. If the determinant is zero, you use a different method. Or there might be a possibility that I have made a mistake, or you have made a mistake, and the determinant is not equal to zero. But in principle, yes, it will happen sometimes that you get a zero determinant. In that case, well, for that,
Okay, so if I get a zero determinant in the exam, I'll be needed to use
there
another
will
method
be
to finish
questions set that
to get the
you
final
will
answer.
know. So if you get a zero determinant in the exam, you know this method doesn't work, this method doesn't work, the third method, I have to use the third method, and that's it. Zero determinant simply
Thank you
tells
so
you
much.
that this doesn't work, but there's another that does work. It will help you choose the method. Okay, so we multiply in this case back to inverse matrix method. Supposing the inverse matrix exists, of course, we multiply from the left-hand side, of course, both sides of the equation. We have a Toggle, please switch off the mic. If you're asking something of me, then yes, but if you are not asking something, should I wait until you finish your conversation? Okay, so please keep your microphone switched off, and sometimes they get switched on accidentally, but just try to look after them. So we have this matrix equation. The system is written in the form AX equals B, and then we come with the inverse, supposing it exists, the inverse matrix of A, and we put it on the left-hand side to multiply. A inverse multiplied. So we understand, of course, that the product of matrix inverse and the matrix itself is the unit matrix, the identity matrix I. So X remains, and here we have this matrix product A inverse times B. But we know that the identity matrix is such that if you multiply identity matrix by another matrix, it changes nothing because identity matrix serves as the number 1 for matrices. And so we have the solution matrix evidently can be found if you multiply A inverse from the left by the right-hand side column, and that's it. So the big work here, so in the previous method, the big work was finding for determinants. The big work in this method is finding the inverse matrix. You have to know how to find the inverse matrix. That would be the big work. So you can never get it very quickly. You always have some work to do. It's not immediate. It's not something that just happens. The good news is that you don't have to write this all the time. So what you do is you have the system AX plus AX equals B. You check the determinant. If the determinant is 0, you know that the inverse will not exist. So yes, we still need determinant that is not equal to 0, because only then the inverse matrix exists. So you check the determinant is not 0, then you find the inverse matrix, and then you multiply this inverse matrix by the column matrix B. And this method says that now you have found the solutions. Now you have found the solutions. So there's no need to write all this. This is simply an explanation at the moment, that is today, about why this method actually works. I think I have the same thing printed. Identity or unit matrix times X is the same as X. So A inverse times B. Basically, let's say the theoretical part is very short. We have this, and we know that to find the solution, we must do this. And that's it. And to find the inverse matrix of A, of course, we need the determinant. Check that it's not equal to 0. If the determinant of A is 0, then A inverse does not exist, which means no, we cannot find the solutions. And when we cannot find the solutions, it might mean that there are no solutions, or that there are, let's say, more than we can manage. And so let's have an example. If we have a system like this, for instance, the system matrix then would be 3, 2, 2, reading the coefficients, 1, minus 2, 1, and minus 1, 1, minus 1. Now to get the system determinant, we would need to find the inverse matrix. We would need to do it for the system determinant. Right at this moment, I want to save us a little bit of time. This matrix actually is something that we already have seen. We found the determinant of this matrix that was equal to 1. We actually found it at some moment. Or was it, don't remember, or maybe we did not. And then we find this, okay. Yes, we found the inverse matrix indeed. We found the inverse matrix at the moment where we did the row reduction method. We had this matrix A or M, and we then had this unit matrix on the right hand side last time. And we used this method to find the inverse matrix. This is what we found by these transformations, the row reduction method. We already have this matrix. That's why I chose this matrix actually for this example, so that we can save some time. We did find the inverse. We did find the inverse last time. It's this. And so now the B for the system of equations, the B column is this, 1, 0, minus 2. So the X should be A inverse. So A inverse 1, 4, 6, 0, minus 1, minus 1, minus 1, minus 5, minus 8. A inverse multiplied by B. And B is 1, 0, minus 2. And now what we have is to find the first element of this matrix X. We need to take first row and multiply it by the one and only column. So it is 1 times 1 plus 4 times 0 plus 6 times minus 2. The second element, second row, we take the second row and multiply by this column. That would be 0 times 1 minus 1 times 0 minus 1 times minus 2. And the third element would be the third row multiplied by the same column. Minus 1 times 1 minus 5 times 0 minus 8 times minus 2. And so we have 1 minus 12 is actually minus 11. Here we have 0, 0, and just 2. And here we have minus 1 and plus 16 is actually 15. And this is the solution. So I can say that X is minus 11, Y is 2, and Z is 15. Or if we write it as the ordered set, minus 11 to 15 is the solution, the answer. So I saved a little bit of time now because I avoided finding the inverse matrix directly. Right now we still have, yes, we have half an hour. So we have gone through 2 methods. And now what we will do, we will just consider some examples for both methods. Just some examples. Oh yeah, there we have the answer again. So let's try Cramer's rule for this. This is exercise 4 from 5A from the lecture sheet, from the lecture file. So in fact, you can do them independently as well. Of course, I cannot do everything in class, but we can do some things. So for this, the determinant, the system determinant would be 2 minus 1 minus 3, 3, 4 minus 5. And now be very careful, the Z is missing, so we have 7, we have 2, we have minus 7, and we have 0, because the Z is missing in the third row. So we will be able to find this determinant. How we find it, how we simplify things, it's completely up to you by what manner you find this determinant. So if we are in a hurry, we could simply um, mm, use the diagonal method, the diagonal product method, or we can use the classical method. After all, let's recall the classical method. So it's 2 times its minor 4 minus 5 minus 7 0 minus, remember, plus minus plus minus plus minus plus minus plus the sign diagram. I'm expanding through the first row. Oh, I could do it through the third row because it has a 0 in there. Also a possibility. Through the third row, I would have plus term 0, so perhaps that's better. Okay, I am going back a little bit. So 4 minus, no, if I'm expanding through the third row, if I'm using the third row, so that would be this 2 times its minor, and its minor is minus 1, minus 1, minus 3, 4 minus 5, minus now, minus negative 7, because it's in the minus position, minus negative 7, and its minor is 2, 3, 2, 3, minus 3, minus 5, and then I have plus 0 times something, I don't care what, because it's 0. And so we have 2, so we have 2 times 5 plus 12 plus 7 times minus 10 plus 9. And so this would be 17 times 2 is 34. 34 minus 7 is 27. Yes, that was the correct answer, I think. Yes. Now the x determinant, I simply replace the first column by 3 minus 8, 17, huge numbers, and the remaining 2 columns stay as they are, minus 1, 4, 7, minus 3, minus 5, 0. So looks like we have to use 17. All right, let's expand through. Okay, we can use again the third row. What's the problem? No problem. So it's 17 times its minor, minus 1, minus 3, 4, minus 5. Then we have minus 7, and now wait. It was minus 7. Here I had hidden the minus under the line. So it's minus 7, I'm very sorry. So it's again minus negative 7. It's in the same place. And it's now a bit different because the first column has changed. So it's 3 minus 8 and minus 3 minus 5. And again plus 0 times something. So we have 17 times 5 plus 12, more 17s. Let me see, minus 1, 4, yes, and yes, that's correct. So we have 5 minus 12, that's plus 12, plus 7 times minus 15 minus 24 is minus 39. That will be an ugly number. As we can see, it's going to be 17 squared, 289, minus 210 and 63. That would be 273, so that's 16. So we already see that the first term is 16 over 27. Yes, I know in this case the numbers did not divide out perfectly. That's true. That's actually correct. That's how these numbers worked out. The y determinant, we leave the first column 2, 3, 2 as it was, but the second column now is replaced by 3, minus 8, and 17. And the third column is again back to the normal, minus 3, minus 5, 0 as it was. So this is an 8. Just not confuse things. No, I don't like the 17, although I'll probably need it anyway. I will have to use it. I will expand through the third column. I will expand through the third column. I choose third column because it contains a 0. So minus 3 is in the plus position, so it stays as it is, and multiplied by 3 minus 8, 2 and 17. Then I have 5. Minus 5 is in the minus position, so it's minus negative 5 times its minor, which would be 2, 3, 217. And finally, plus 0 times, again, because I don't even write this 2, 3, 3 minus 8 because it will not make any difference. So we have minus 3 times 51 plus 16, plus because I'm subtracting a negative number, plus 5 times 34 minus 6, that's 28. And so we have minus 3 times 67 plus 140, minus 3 plus 67 is minus 201. So it's minus 61. That's approximately right. And the Z determinant, the first column remains as it was, 2, 3, 2. Second column back to normal in the original matrix. It was minus 1, 4, minus 7. And now for the third column, I replace 3, minus 8, 17. Now, by whatever method we have to find the value of this determinant. We could make some zeros or not. That's our choice. So I would say, so do we want to make zeros? Supposedly yes. Row 2 plus 4 row 1 will make a 0 here. Because I have this minus 1, I find it very convenient to multiply it by 4 and add it downwards to eliminate 0, to eliminate 4 below it. So we have 2 minus 1, 3. Now first row times 4. 2 times 4, 8, plus 3 is 11. Minus 1 times 4 is minus 4, plus 4 is 0. 3 times 4 is 12. 12 minus 8 is 4. And for the third row, looks like I could say row 3 minus 7 row 1, because minus 1 times minus 7 will make a 0 if we add it to the minus 7. So minus 14 plus 2 is minus 12. Minus 7 times minus 7, 7 plus minus 7, 0. 3 times minus 7, 3 times minus 7, yes, no problem. If you want to start writing the solutions or anything, that's absolutely fine by me. So 3 times minus 7 is minus 21, plus 17 is minus 4. So now in this case, we see that we only have to take this, which is in the minus position, so it becomes plus 1, and multiply it by its minor, which is 11, 4, minus 12, minus 4, and we have minus 44 plus 48 looks like a 4. And so the solutions would be x is 16 divided by 27, y is minus 61 divided by 27, and z is, looks like 4 over 27. Something like this. I might have made an arithmetical mistake. I might have made an arithmetical mistake. Z is 4, yes. The last one is 4. Minus 61, yes, and just 4, yes. Okay, yes. I understood that you pushed an extra 4. It's 4. So we have the solutions. So you see, if we try to solve this system in a different way. For example, we try to express, let's say, take I don't even know. Take y from the first equation, express it through x and z, and then put it into the second and the third equation. Then you have two equations in two unknowns only, x and z, and then you solve that mini system, and then you go back and find y. And all these solutions are unpleasant fractions. So in the case where the solutions are unpleasant fractions, it's actually the Cramer's rule is actually very convenient because then all you have to do is find the determinants, write down those fractions. If you solve it classically by the classical methods, it's much clumsier, messier, and less pleasant. So Cramer's rule actually also
Madam,
works. Yes,
hello, ma'am.
yes.
Can we do any method in exam? Is that our choice?
Let's put it this way. Let's put it this way. In the midterm examination, you will be able to choose. Right now, next week in the unit test, I want to check all the methods, and therefore the questions will tell you which method to use. The first one will be Cramer's rule, this one. The second will be inverse matrix method, and the last one will be the method we study on Monday, Gauss method. Because I need to test all methods, because testing all methods basically shows me whether you understand matrices as well. I don't have to do extra exercises for you, extra questions about matrices. It's only about these. But in the midterm examination, you may choose whichever method you find better, as long as it's a matrix method, something from this, not something where you express one variable from one equation, then put it into the other equations and mess around like you did in school perhaps. Because that's really messy. That is really messy. With determinants, at least we know exactly and precisely all the time what we have to do. More Cramer's rule, more. Okay, I'm leaving that Cramer's rule because we have something like 15 minutes remaining. Let's move on to the inverse matrix method actually, because inverse matrix is also something that needs to be, let's say, revised, because we just learned the inverse matrix, so it might not be so strongly in your memory yet. So the inverse matrix method, find the inverse matrix of this and then solve the system this. So using the inverse matrix method, in this case it would be a 2 by 2 matrix. Let's remember the inverse of a 2 by 2. First of all, the determinant of this matrix would be 28 minus negative 72, that's 100. That's a good determinant because it's actually simple then. Now the inverse matrix itself, let's remember it was 1 divided by determinant, and then we had to work with the adjoint matrix, and for 2 by 2 it was easy. 4 and 7 simply swap places, and the other two elements simply change signs, from -9 to +9, and from 8 to -8. So this is the inverse matrix. I could multiply the 0.01 into the matrix, but I won't do it at the moment. I will leave it to the end. And now to find the system solutions, remember that X is inverse matrix times B, and the matrix B is, as we see, 50, 24. So we have 100, 7, 9, minus 8, 4, multiplied by 50, 20.
Yes, I have a question. question, right? So in the exam, if we get a um, simultaneous equation of two equations, are we do we need to use the matrix method?
Yes, because the only reason I might give you a system of two equations is that there are numbers so unpleasant that Cramer's method is the best. So I might deliberately give you nasty numbers like 289x minus 701y, for instance. So yes, matrix method. Because we are studying linear algebra, we are studying matrices, which is the main point. School methods, sorry, I'm not accepting school methods at this moment because matrix methods are important, let's say, on a greater scale. And so multiplying. So I'm starting by multiplying these, and then in the end, I will multiply by 100. So 7 times 50 is 350, plus 9 times 24 is 180, and 36, 216, I think. Now, minus 8 times 50 is minus 400, plus 4 times 24, that's 96. And so I see it's 1 over 100 times 566, right? 566. And here we have minus 304. And so now multiplying by 100, I have 5.66 minus 3.04. And these are the solutions. This is the solution matrix. So I can say that x is 5.66 and y is minus 3.04, and that's it. I chose 2 by 2 for this method simply because, well, in a sense, at this moment for this exercise, the inverse matrix of 2 by 2 is easier to find. It's easier to find. 2 by 2 inverse matrix is simple to find, so it's not a waste of time. However, in the test, you will have a 3 by 3, so we have to do the inverse matrix method properly. You may choose how you find the inverse matrix. Cofactor method works very nicely, or you could use this double matrix thing and try to change it into the unit matrix. That's an option always. But let's just do the cofactor method. In either case, we would need to look at the determinant. In either case, we would need to look at the determinant, and then, yes, the goal is to solve these two systems. Notice that the left-hand side of each system is the same. The left-hand side of these systems is the same. The right-hand side is the only thing that changes. So we will be able to use the same inverse matrix for both. And that's what I hope to do in the coming 10 minutes, upcoming 10 minutes, and then we can finish. So finding the inverse matrix of this, let's remember the cofactor method. So the determinant of this matrix, all right, there are zeros, so all right, 2 zeros is fine, or we can have 1, 0, 2, and minus 3, 3, minus 1, and we can have this is 6, this is minus 6, and this is 0, right? 6 minus 6 plus 0 minus, and now the negative, so this is 0, this is minus 1, so we have 0, minus 1, and we have 0 again. This is 0 again. So in principle, we see it's 0 minus negative 1. The determinant is 1 of this matrix. So that's good because that won't give us any problems now. The determinant 1 divided by 1 will be in front of the cofactor matrix. That's not a big problem. So now let's see the cofactor matrix. Remember, we replace each element by its cofactor. So the cofactor of, I will erase, in fact, I will just erase these lines so that we are not confused with them if we have too much on the board. So the cofactor of the first element is 3, 1 minus 1, 2 for this. For the next element, remember we have a minus in front. So the cofactor will be 0, 2, 1, 2. We use the elements that are not in that row and not in that column. The third cofactor without a minus again will be 0, 3, 2, minus 1. Remember that the cofactors do not involve exactly the elements themselves. When we are finding the determinant, then the cofactors will be multiplied by the elements. But as they are only the small determinants with plus or minus sign. So minus position will be minus 3, 0, minus 1, 2. The central position is a plus position. Cross out second column, second row. We have the corner elements 1, 0, 2, 2. Now, second row, third column, crossing it out and with a minus sign in front because we are in the minus position. 1 minus 3, 2 minus 1. And the last row, for the bottom left element, the minor is minus 3, 0, 0, 1. For the next, minus 1, 0 vertically and 0, 1. And for the last one with the plus position, 1 minus 3, 0, 3. So at this point, what matters is to be able to write down those cofactors. Now we will see what the cofactor matrix actually is. This is the cofactor matrix, and we should always write it down because it's too easy to make a mistake if we don't write it down. I know it's possible some people, let's say who are very good at mathematics, want to do it all in your head. I can tell you that it's very, very easy to get confused. If you are not seeing those four numbers separately, it's very easy to make a mistake and grab a wrong number. I really don't think it's a very good idea. So 6 minus negative 1 is 7. 0 minus 2 is minus 2, but another minus in front makes it a plus 2. 0 minus 6 is minus 6. Now the next one, minus 6 minus 0 is minus 6. The minus in front now makes it positive 6. The minor itself is negative, but we have an extra minus in front, right? So in the middle, 1, 2 is 2, minus 0, still 2. Here we have minus 1 plus 6 is 5, and minus in front makes it minus 5. And then we have minus 3, and then we have minus 1, and then we have 3. This is the cofactor matrix. So the inverse matrix, okay, let's suppose this is the matrix A. So A inverse would be 1 divided by determinant. I'm putting 1 simply to remind you that, yes, we do need to put this in front. There are many cases when people simply forget. It's very easy to just forget that we had to multiply by 1 divided by determinant. That's why I'm writing it down now. And then we have transpose 7, 2 minus 6, but in the column instead of row. 6, 2 minus 5 in the second column instead of second row. And minus 3 minus 1, 3 in the third column instead of row. And now, to solve this, we have to make sure, first of all, let's check the matrix. 1 minus 3, 0. Yes, 1 minus 3, 0. Now for x, we have a 0 coefficient, 0, 3, 1. For this, 0, 3, 1, it's correct. And the last one, 2 minus 1, 2. 2 minus 1, 2. Yes, indeed, this matrix is the system matrix of these two systems. So all that we have to do is multiply by the relevant B columns. So for the first system, I have to multiply I have to multiply this inverse 7, 6 minus 3, 2, 2 minus 1, minus 6 minus 5, 3. I need to multiply this by the column matrix 2 minus 2, 1. And that would be 2 times 7 is 14, minus 6 times 2 is minus 12, and minus 3 times 1 minus 3. Second row, 2 times 2, 4, minus 2 times 2, 0, and minus 1. So 4 minus 1. And finally, 2 times minus 6 is minus 12, minus 5 minus 2 is plus 10, and 4 times 1, no, that's 3. 3 times 1 is 3. So the solution of the first system is 14 minus 15 minus 1, 4 minus 4 minus 1, again minus 1, and minus 12 plus 13 is 1. And you can, at any moment, you can check and you can see how if you put these numbers instead of x, y, z, you will get a true system, a system of true equalities. And for the other one, for the second, we take the same 7, 6 minus 3, 2, 2 minus 1, minus 6 minus 5, 3. The left hand side is the same, and the column matrix is minus 2, 7, and 7. So we will have minus 14 plus 42 minus 21. So I multiplied first row by the column. Now second row by the same column is minus 4 plus 14 minus 7. And the last row through this column would be 12 minus 5 times 7, that's 35, plus 3 times 7, that's 21. And we have 42 minus 35, that is 7. Minus 11 plus 14, that is 3. And 33 minus 35 is minus 2. And again, you can just take these and put this solution to check in that system, simply to verify that you have found everything correctly. So this is how the inverse matrix method works. In principle, finding the inverse matrix, once you understand the minors and cofactors, finding the inverse matrix actually is not difficult. The difficult part is not to confuse the minus positions, to write the minuses. Second thing is copying the cofactors correctly, because it's very easy to grab the wrong numbers and put somewhere there. So, so for example, if I have the corner elements, that's easy. But if I have an element that is in the middle of a row, then it's rather difficult to get the correct cofactor. So just be careful when writing down cofactors. And here we are. So you can already start solving your homework, your home assignment. You can find, each of you has an assignment, a task by name, and each task has a 4-digit number, code number at the bottom. That's because I have many versions. I have a large collection of these homeworks, and you have to write down this code number in the file name so that I know which
Yes, I just want
answers.
to ask you a question. Is this only total of 5 questions? There's 5 questions?
This is the home assignment that I have uploaded in Arcus already.
Yeah, I see it. I only seen 5 questions. So I just want to make sure it's only
Oh,
5 questions.
that's an A5 page. It's like half a large page, half of an A4 paper. Yes, it's what you see there. It's each page of that file is for one person, and that's it. And
Thank
so
you,
the
ma'am.
Ms.
food.
Vikram.
And the 4-digit number has to be put in the file name. Next, there is an
Ma'am, can
assignment in Ortus. I don't know. You should learn. You should be able to find the assignment. So those who are new to RTU, those who are new to Ortus, there is such a thing called assignment where you can upload your finished papers. When you take pictures, you create a PDF file or scan. For example, you can upload that file to the assignment folder. It's in Ortus. It's in Ortus. My Ortus looks different from yours a little bit, so I can't really post pictures. But if you have problems, you could also put in search assignments in your math course, for example, assignments, and it will show you. So you can upload there the finished work, only one file, so it has to be one single PDF file. And please put the questions, the answers to the questions, in the correct number order. For example, one possibility, when you take pictures, you just put those pictures in the correct order in the PDF file. Another possibility, take a pair of scissors, cut up your paper, and place the pieces in the correct order. That's another possibility. And please take the pictures normally and put it upside up in the file, because it's very, very difficult for me to correct them otherwise, because the Moodle does not allow me to rotate the pictures, to rotate the images. So this means the image really has to be upside up. And please make it good quality, readable quality, because otherwise again I can't really read or correct anything. So you have a whole week to do this. It's actually, as I said, a good practice before the unit test. That's one of the main reasons I have them. And then next week on Monday, I will talk a little bit more about how we take unit tests. You have a week time to learn how to adjust your webcam so that I can see your face and your hands as you write. That's a requirement, and I know that it's not always simple if your desk is small and your camera is closed and you can't really adjust so that everything is visible. So it takes some effort and adjustment. So that's why you have a week to do that in practice. Right. I will see you on Monday then. We will
hello,
do
ma'am.
what?
I have not assigned the home assignment. I am not getting my name.
Why? Is this the first
No,
time you show up in a lecture?
no. I have been since the first lecture.
Then you should have your name in there. Okay, if I have made a mistake, email me please. I'll check and see. I'll
Okay,
check
okay.
and see. I
Ma'am,
thought I thought I got the number right.
can you provide the Otis homework answers?
Answers for homework? No.
The exercise
The homework,
exercise.
that's why you have individual homework, so that you
Not
do
that
it and I correct it.
not that, madam.
What then?
The exercise in lecture note.
It is in the lecture notes. I changed
Okay.
two files which had unfortunately no answers,
Oh,
so number 2, number 3, yes, but the other files
okay.
should have answers in them.
Okay.
So first of all, actually, you should check before you ask that kind of questions. Check that they are really not there, and then ask me for the answers. Okay, so I guess once the semester starts more seriously and picks up speed, then we will be better with this. All right. On Monday, we will have the remaining method. We will see how to deal with situations where determinant is 0 or worse, does not exist, because the matrix is not square, the system is not square. We'll look at examples and how to deal with those situations, and that will be generally it. In principle, on Wednesday, we start the new material already. That would be vectors, vector algebra, more than vector geometry, more algebra than geometry. All right. Have a nice. What does verify the result of by the definition of inverse matrix? What was the definition of inverse matrix? It's the matrix whose product with the given matrix is the unit matrix, the identity matrix. In other words, you find the inverse matrix by this method, by cofactors, for example, or maybe by row reduction, the thing we did last time, and then you multiply by the original matrix to check, do we get the identity matrix? That's verifying. That's checking. Okay. All right.
Yes,
One
I
more
have one
question.
more question. The test, will it be like it will be on authors and you have like a time and
No. You will
uh,
log in. We will have a Zoom meeting. I have at the moment. I'm splitting you into three groups, so approximately 20 people in each group. So I will see 20 of you on my big screen with your cameras, and I will share screen with the questions. Three questions, so they are easy to put on screen, and also perhaps some essential information about matrices, so that well, like a small formula list that you might need. So basically, the questions and the formulas will be on the screen.
so you will give us the formula sheet, right?
That's not homework. Homework. What mess are you? What's missing? What messy thinking do you have? So I already said that the unit test has three questions. The time is 40 minutes plus 10 minutes to set up the file and upload, because I understand that for in the first time, if you have never done this before, you might probably need some time to set it up. Although you can practice at home that you know how to make a PDF file quickly from some images of your work, you can practice a little bit to just to try to do this. 40 minutes for the whole unit test. So we start. You have 40 minutes, and then you have 10 minutes for the upload to create the file and upload it. So altogether 15 minutes. So if you practice before and if you know how to make the file quickly and well and upload it correctly, if you have practiced in advance a little bit how to access the assignment, you know where to do it, then you might have, let's say, 5 minutes extra for writing. If you know how to make the file very quickly, then out of those 10 minutes, you might have a little bit of extra time. But in general, it's 40 minutes for three systems of equations. So two systems will be like this, one with inverse matrix like this, and another with Cramer's rule like the one before, and the third one will be something we discuss on Monday. And I think 40 minutes is quite enough for that. All right, have a nice weekend. I am signing off now.
Thank you, ma'am.
Thank you so much.
Okay, thank you for the lecture.
You're welcome. Hope you signed up
Thank
in
you,
the.
Thank you, man.
Thank you, ma'am. Have a nice day.
Welcome. You're welcome.
Bye, ma'am.
Bye.
Madam, so do we get everything on the tools?
Yes,
Okay,
everything
thank
is
you.
noticed.
All right, thank you for the lectures.